Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good morning to everyone. So, for the first all, my name is Nabil Zarif Bin Salleh from MT2 with IC number 0606050211 and 17. So today, I'm excited to present my project titled Optimization of Delivery Routes Using Heuristic Methods for course MTES1142 Computational Thinking in Mathematics at Institut Pendidikan Guru Malaysia, Penang Campus. So, everyone, in this presentation, which I will run for approximately 10 to 20 minutes, I will cover the challenges of delivery route optimization in the logistic industry, explain several heuristic methods that help solve such complex problems, and compare the performance of these methods under specific operational constraints. So, everyone, before we get into the technical problems, I would like to briefly discuss why this topic is so important. Efficient routing directly impacts operational costs, delivery time, and overall customer satisfaction. Even a small improvement can lead to significant savings in fuel and labor. Throughout this session, please feel free to jot down any question. We will have a Q&A session at the comment section. So now, let's move on to the background and context of our study. So guys, efficient optimization is crucial in the logistics industry. With rising fuel costs and increasing delivery demands, companies must ensure that every route minimizes distance while meeting time and capacity constraints. This challenge is well represented by the traveling salesman problem, or we call it as TSP, where the objective is to determine the shortest route that visits a series of cities once. However, our problem is even more complex. Not only do we have multiple stops, but our trucks must also adhere to specific constraints, such as making at least 3 stops before arriving at the final destination, which is Kuala Lumpur. So guys, TSP is classified as an NP hard problem, meaning that as the number of locations increases, the number of possible routes grows exponentially. This is why exact solutions are impractical for large problems. And heuristic methods, approaches that provide near or optimal solutions quickly, to become invaluable. For example, imagine a scenario where a slight improvement in road efficiency saves just 2% in fuel costs. For a company running hundreds of trucks, this translates to significant savings. So, I would like to ask you everyone, how many of you are familiar with NP hard problems or have encountered the TSP before? So guys, please provide your answer in the comment section. So, in summary, our project leverages heuristic methods to tackle a real-world version of TSP tailored to logistics with extra constraints. So guys, our research is built on 4 main objectives. So for the first one is identify 5 heuristic methods applicable to optimizing delivery routes. So for the second one is compare the effectiveness of each method in terms of distance, cost, and truck utilization. So number 3 is analyze key performance metrics such as fuel cost and operational time. So the fourth one, recommend the most suitable heuristic method for practical logistics applications. Each objective is critical. For instance, even a minor improvement in road efficiency can result in significant savings in fuel costs and time. During this session, I will detail how each method contributes to this objective and provide examples from our calculation. So guys, this study will evaluate the following 5 heuristic approaches. So for the first one is greedy algorithm. So the second one is simultaneous annealing, or we call it is SA. So the third one is genetic algorithm, or we call it is GA. The fourth one is branch and bounce, or we call it is BNB. And the last one is end colony optimization, or we call it is ACO. So guys, let's now move on to define the specific problem and parameter of our study. So guys, let's define our problem in practical terms. Our scenarios involve a logistic company that must deliver goods to 7 different locations using 10 trucks operating from 5 distribution centers. So each truck has a 10-ton capacity and can travel at 60 km per hour, operating for a maximum of 10 hours per day. The fuel cost is 2 ringgit and 50 cents per kilometer. A significant new constraint in our problem is that every truck must stop at a minimum of 3 different destinations before reaching Kuala Lumpur. This constraint is particularly challenging because it forces the road to include intermediate stops that might not otherwise be on the shortest path. So this multi-constraints problem requires advanced optimization techniques. So our approach is to apply various heuristic methods to see which method best meets these requirements. So both in theory and in practical cost saving. So everyone, let's discuss. How do you think adding a minimum stop requirement might affect the overall road? So please provide your answer in the comment section. So these are the parameters set the stage for our analysis. And in the next slides, we will look at the methodology we used to tackle this problem. So guys, our methodology follows a systematic approach. First, we construct a distance matrix, which is essentially a table listing the distances between all the key cities involved. So this matrix forms the foundation for our route calculations. So next, we apply 5 different heuristic methods. So for the first one is the greedy algorithm. Is a simple method that always chooses the nearest neighbor. The second one is simulated annealing. Introduces randomness and uses a temperature parameter to escape local optima. Branch and bound systematically explores all possible routes, pruning those that exceed a certain bound. And colony optimization mimics the natural behavior of ants to reinforce shorter routes through pheromone deposition. So the last one is genetic algorithm, uses natural selection principles, crossover and mutation to evolve a population of routes toward the optimal solution. So guys, finally, we compare the results of each method focusing on total distance traveled, fuel cost and truck utilization. This methodology not only provides a robust comparison of different techniques but also highlights which method is best suited for our logistic constraints. So guys, here we have our distance matrix, which is critical to our analysis. This table shows the distances between our key cities. For example, the distance from Alor to Sungai Petani is 60 km and from Sungai Petani to Butterworth is 50 km and so on. This matrix allows us to calculate the total travel distance for any proposed route. It was compiled from historical data and verified for accuracy. So understanding these distances is essential because every heuristic method we discuss will use this data to calculate and compare different routes. So please take a moment to look at the table. So if you have any question about how these distances were determined, please feel free to ask now. So everyone, let's examine the greedy algorithm first. So this algorithm is simple. It always selects the nearest university city starting at Alor. We choose Sungai Petani because it's only 60 km away. So next, from Sungai Petani, we select Butterworth, which is 50 km away. Continuing this process, we travel from Butterworth to Ipoh, which is 160 km, and then from Ipoh to Kuala Lumpur, which is 200 km. So this results in a total distance of 470 km. So with a fuel cost of 2 ringgit and 50 cents per kilometer and using 10 trucks, the total fuel cost is 470 kilometers times with 2 ringgit and 50 cents per kilometer and 10 trucks, which is we will get 11,750. So while this method is quick, its main drawback is that it makes decisions based only on the nearest neighbor and may not find the optimal global route. So guys, I would like to ask you guys, what do you think might be a limitation of this approach? Please provide your opinion on this comment section. So guys, this simple method is a good starting point but often needs further refinement. So guys, continue from the greedy algorithm. Simulated annealing is inspired by the physical process of annealing in metallurgy. We start with the greedy route as our initial solution. Then we randomly select two cities and swap their order to create a new route. For example, if we swap Sungai Petani and Butterworth, we might obtain a route like Alostar to Butterworth, to Ipoh, to Seremban, and then to Kuala Lumpur. After this change, we calculate the total distance, which in this case becomes 490 kilometers. Consequently, the fuel cost increases to 490 kilometer times with RM2.50 per kilometer and times to 10 trucks, which is we will get 12,250. The key idea in SA is that even if the new road is worse, the algorithm might still accept it with a probability that decreases over time as the temperature decreases. This allows the algorithm to avoid being trapped in the local optimum. So I would like to explain the temperature concept. Initially, the system is hot, meaning it is more likely to concept a worse solution, allowing a wide exploration of the solution-scape. As the temperature cools, the algorithm becomes more conservative and converges on a stable solution. Does anyone have any question about why we might accept a worse solution early in the process? So guys, please provide your comment in the comment section. Even though in our example, the new road increased the distance, this method is valuable for exploring a wider set of possible routes, especially in more complex scenarios. So guys, branch and bound, or we call it is BNB, is rigorous, systematic method that involves exploring all potential routes while eliminating those that are not promising. Here's how it works. So for the first one, we enumerate all possible routes that start at Alostar and include at least 3 stops before reaching Kuala Lumpur. So for the second one is, for each route, we compute the total distance. For instance, one route might be 470 km long, another 460 km, and yet another 490 km, and the other one is 510 km. So the third one is, we then set a lower bound, which is the shortest distance found so far, and upper bound, the maximum acceptable distance. So for the fourth one is, any road that exceeds the upper bound is pruned, meaning we do not consider it further. So for the last step is, through this process, we eventually converge on the optimal route, which in our example is 460 km. This method guarantees finding the optimal route but can be computationally intensive for large data sets. So the fuel cost for the optimal route is calculated as 460 km times with RM2.50 times with 10 trucks, and we will get 11,500. So guys, I would like to ask you, how do you think setting these bounds helps in reducing the number of routes to consider? So guys, please leave your comment in the comment section. So guys, now we move to another heuristic methods that we use to solve the problems. So the next method is ant colony optimization, which is, we call it is ACO, SACO. So what is ACO? ACO is inspired by the foraging behaviors of ants in nature. Ants deposit pheromones along the path they travel, and over time, shorter paths accumulate more pheromones. Here's how we apply ACO. So for the first one is initially, we assign an equal pheromone level to every possible route. So the second one is we then simulate multiple ants traversing each route. As they travel, they deposit pheromones inversely proportional to the distance traveled. That means the shorter the road, the more pheromones are deposited. So the third one is over successive iterations, pheromone evaporation occurs, which means that routes with less pheromones gradually lose their attractiveness. So the fourth one is eventually the route with the highest accumulated pheromone level is considered the optimal route. In our example, we have we have three types routes. So for the first one, we have first, fourth, and sixth routes are 470 km and is marked and was marked with a medium performance level. And then we have road 2 is 460 km and is marked as high, and then road 3 and 5 are 510 km and are rated as low. So through the iterative process, the road that is 460 km long emerges as optimal. Thus, the fuel cost is calculated as 460 km times with RM2.50 per kilometer and then times with 10 trucks. That's equal to 11,500 ringgit. So guys, I invite you to think about why pheromone evaporation is critical. It prevents early convergence on a suboptimal road by allowing the system to forget less promising solution. So guys, now we move to the last heuristic method that we use to solve the problem. So we use the genetic algorithm, which is we call it as GA. What is GA? GA use concepts from natural evolution to optimize solutions over time. In our case, we begin by generating all possible roads using our set cities, which is Alostar, Sungai Petani, Butterworth, Ipoh, Rawang, and Seremban. Remember, each route must include at least 3 stops before reaching Kuala Lumpur. So, for example, our initial population of roads might include. So, the first road is Alostar to Sungai Petani, to Butterworth, to Ipoh, and then to KL. The second road is Alostar, Sungai Petani, Butterworth, Rawang, and KL. The third road is Alostar, Sungai Petani, Butterworth, Seremban, and KL. The fourth road is Alostar, Butterworth, Ipoh, Seremban, dan KL. The fifth road is Alostar, Butterworth, Seremban, Rawang, and KL. And the last road we have Alostar, Butterworth, Ipoh, Rawang, and then KL. And then we evaluate these roads by calculating their total distances. So next, we select the top 3 roads 1, 2, and 6 in our example with distance of 470 km, 460 km, and then 470 km respectively. So the next step is crossover, where segments from these selected roads are combined. For instance, we might take the first half of road for the second road and the second half of first road. After that, we introduce mutations by randomly swapping stops. These genetic operations generate new variation of routes, and we repeat the process over several generations until the algorithm converges on an optimal solution. After numerous iterations, the GA converges on the optimal road, which is Alostar to Sungai Petani, and then to Butterworth, and then to Rawang, and then to Kuala Lumpur, with a total distance of 460 kilometers. So the fuel cost for this road is calculated as 460 kilometers times with 2 ringgit and 50 cents per kilometer, and then times with 10 trucks, and we will get 11,500 ringgit. So guys, does anyone have any questions about how the crossover or mutation steps work? So everyone, to summarize, our analysis shows that advanced method, which is specifically branch and bound, which is BNB, and colony optimization, which is ACO, and genetic algorithm, which is GA, are consistently find the optimal route of 460 kilometers which correspond to the lowest fuel cost of 11,500 ringgit for our problem, while the greedy algorithm provides a quick solution and simulated annealing shows the potential improvement, neither achieve the efficiency of the advanced method. This result underscores the importance of using sophisticated heuristic approaches for complex logistic challenges. The benefits are clear: reduced fuel costs, shorter travel distance, and better overall truck utilization, all of which can translate to significant operational savings in a real-world context. So guys, I would like to ask you, how might this finding influence decision making in a logistic company? Please provide your comment, provide your answer in the comment section. So, these are the key references that form the theoretical foundation of our project. So they include seminal works on an colony optimization, which is ACO, genetic algorithm, which is GA, and simulated annealing, which is SA, among others. I encourage you to review these sources for a deeper understanding of the underlying principles, noting that each reference has been formatted in MTES11 style, which is essential for academic rigor. If anyone is interested in further details on any of these methods, I'd be happy to discuss them after the presentation. So, this concludes my presentation. Thank you very much for your time and your attention. I hope this session has provided valuable insights into heuristic optimization methods and their applications in logistics. If you have any question or would like to discuss any part of the presentation further, please feel free to leave comment in the comment section. I will respond accordingly. So once again, thank you very much and I appreciate your time. Thank you very much, everyone.